Okay, I'm Kenta Murakami from Panasonic Automotive Systems. Today, I'll present at the latest updates to Unified HMI, focusing on simplified APIs for dynamic multi-display layout control. I would like to take a moment to introduce myself. I'm Kenta Murakami from Panasonic Automotive Systems, and I've been working on Unified HMI development for about 4 years. Since October 2024, I've been contributing Unified HMI programs to AGL UCB. And outside of my work, I enjoy traveling, ramen, and coffee. And as Jerry-san introduced, my baby was born last December, so thank you very much. So recently, my hobby is all playing with my baby. Okay, thank you. Okay, this is today's agenda. First, I'll explain what Unified HMI is and the motivation behind it. After that, I'll move on to Unified HMI architecture to show how it enables multi-display control. Next, I will introduce the key updates in Unified HMI version 3, which significantly improves developer experience by simplifying APIs and enabling dynamic layout control. Finally, I'll talk about Unified HMI on AGL SODEV. In many presentations, introduced Unified HMI is expected to support SODEV, so I will introduce how and when Unified HMI supports SODEV. Okay, let's start with what Unified HMI is. To understand why Unified HMI is necessary for automotive industries, let's first look at recent trends in the car cockpit systems. In recent years, the number of in-vehicle displays has been increasing. Traditional analog devices are being replaced by digital displays, such as digital clusters, infotainment systems, and head-up displays. As a result, there is a growing demand for flexible application layout across multiple displays. However, with conventional graphic frameworks, supporting these requirements often means developing ad hoc coordination for each car grade and model. This is because hardware configurations, SoCs, and operating systems on it can vary significantly. So this increases complexity and development cost, and this is exactly the challenge we aim to do. So to address these challenges, we developed Unified HMI. Unified HMI is a software-defined display virtualization platform based on VirtIO-GPU. It allows for flexible layout control of applications across multiple displays, independent of hardware and OS configurations. With Unified HMI, you don't need specific modifications for each application, so the same application can be reused across different car grades and models, and you can continuously update it for them for the future car grades and models. So now that I've explained what Unified HMI is, and next I will introduce the internal architecture. Unified HMI is composed of 2 main components. The first component is Remote VirtIO-GPU, which we call RVGPU. RVGPU enables applications to be rendered remotely on different SoCs or virtual machines, even when different operating systems such as Linux, AGL, Android are running. The second component is Distributed Display Framework, which we call DDFW. DDFW is responsible for launching applications and controlling their layouts across multiple displays and managing their lifecycle. In other words, RVGPU virtualizes GPU rendering across nodes, while DDFW provides system-level control over where and how applications appear on the displays. By combining these 2 components, Unified HMI can flexibly control multi-display layouts independent of hardware configurations and operating systems. Okay, let me start with RBGPU explanation. Which is the core technology that enables remote rendering in Unified HMI. RBGPU is a network extension of VirtIO-GPU, which commonly used for GPU virtualization in virtual machines. This diagram shows a graphic data flow when using RBGPU, from application execution on the sender side to rendering application on the receiver display. When applications are rendered using this, on the sender side, the VirtIO loopback driver creates a new VirtIO GPU devices on the sender. And when applications are rendered using this device, GPU commands generated by OpenGL are captured and transmitted to RBGPU proxy on the sender side. Then, RBGPU proxy sends GPU commands and texture data to RBGPU renderer on the receiver side over network. On the receiver side, RBGPU renderer processes them and renders application graphics using the local GPU, following the standard rendering pipeline. Input events such as touch and pointer interactions are also transmitted back to the sender from receiver display, so allowing user to interact with remote applications seamlessly. As a result, applications can run on one SoC or virtual machine, while their graphics are rendered on different SoCs or virtual machines. This slide shows how Unified HMI could control layouts of multiple applications. In Unified HMI, the RBGPU renderer on the receiver side is responsible not only for rendering, but also for compositing multiple application windows and controlling their layouts transmitted by RBGPU proxy. RBGPU renders all applications into a single surface, so the window manager only needs to attach this surface on it. So it's possible to support various operating systems without specific plugins for each. As a result, flexible and consistent multi-display layouts can be achieved across heterogeneous systems using a single layout control mechanism. So far, I've explained how layouts can be controlled at the rendering level. So next, I will introduce DDFW, which manages layouts at the system level. DDFW maps multiple physical cockpit displays into a single large virtual screen, like this figure. Applications can be placed and resized on this virtual screen, independent of the actual hardware configurations and arrangement. Then, DDFW can control their positions and sizes across multiple physical displays. In addition to layout control, DDFW also manages the lifecycle of applications and RBGPU modules. When using DDFW with RBGPU, developers could focus on layout design at the system level rather than dealing with individual complex display management. DDFW consists of two main components: Unified Clustering Tools, we call UCL, and Unified Layout Tools, we call ULA. UCL is responsible for managing the overall lifecycle of applications and RBGPU modules, such as launching and stopping them across SoCs or virtual machines. ULA, on the other hand, provides unified control of application layouts across multiple displays. As shown in the diagram, both UCL and ULA share a similar architecture. They provide gRPC-based client APIs that can be implemented in any application, regardless of the programming language, by using gRPC protocol. APIs send commands to manager components, and the manager interpret configuration definition in JSON file and generate detailed instructions. Then, These instructions are transmitted to worker nodes and they execute actual tasks like stop or run application. This architecture provides strong flexibility and clear separation of responsibilities. However, it also means developers need to deal with multiple components, UCL and ULA, separately, so it leads to operational complexity. This is one of the key motivations behind the updates for Unified HMI version 3. Let's move on to the updates in Unified HMI version 3. Unified HMI version 3 focuses primarily on usability and developer experience. First, we introduced new simplified APIs that reduce manual steps and JSON handling for developers. Second, we will add the Unified HMI support on AGL SODEV. In detail, we will support Zen hypervisor on Sparrowhawk board. Third, we will support new use case, including combination with AGL and Android to support SODEV use cases. For example, render AGL applications to Android display and control layouts of them. Together, these updates make Unified HMI more practical for real-world multi-OS, multi-display development. To simplify architecture for easy integration, Unified HMI version 3 merged UCL and ULA into a single UHMI module. This significantly reduces the number of components developers need to interact with. Version 3 mainly consists of 3 parts: UHMI API, UHMI master, and UHMI worker. The UHMI master manages application lifecycle and the layout control, while UHMI workers handle execution and rendering on each node. This simplified architecture allows us to provide simpler APIs and reduce manual operational steps for integration. Also, Unified HMI version 3 enables dynamic layout control without JSON files. As a result, Unified HMI version 3 significantly reduces manual operations and allows developers to more focus on UHMI design and UX rather than system integration. In this slide, I will explain how Unified HMI version 3 enables dynamic layout control without relying on JSON file at runtime. First, I want to clarify one important point. While runtime layout control no longer requires JSON files, a display environment definition JSON file is still necessary. So this file defines the virtual screen and the available display areas, and it is created once before starting Unified HMI as a presetting. After that initial setup, layouts can be controlled dynamically while applications are running using simple APIs with animations. In version 3, we introduce custom display areas on the virtual screen like display area 1 in the below diagram. These areas work like virtual displays, and the developers can freely define their size and position in the display environment definition files. As shown in the right diagram, by using these customized areas, APIs such as Move Up and Wide Up can place applications on a specific area or span them across multiple displays without loading any layout JSON files at runtime, independent of OS and hardware configurations. I explained you have to make a display environment definition JSON file. So to minimize this effort, we provide a web-based JSON creation tool which can support its creation with very simple GUI. With this tool, developers can define display environments using simple input forms like left side figure, such as node information and display resolutions and virtual display arrangement on a canvas And visually, you can visually arrange virtual displays on the single large virtual screen using the mouse. This allows developers to create the required JSON file without manually editing complex configuration files. Once the environment JSON is created and deployed, developers can launch Unified HMI version 3 APIs for dynamic layout control. This slide compares API usage between Unified HMI version 2 and version 3. With Unified HMI version 2, launching an application and controlling its layout required 3 steps and several JSON files. In detail, first, developers need to launch RBGPU receivers on the receiver by UCL command. Then, applications were started by UCL command using an application configuration file. Finally, ULA layout commands were applied by loading additional JSON files. While this approach was flexible, it also introduced operational complexity. So with Unified HMI version 3, this workflow is significantly simplified. Launching an application and controlling its layout can now be done with a single command without relying on JSON command at runtime. Developers only need to specify the application name and the target display. We also provide advanced commands as API options. For example, move up can move application to the indicated displays at runtime, and animation up can move application dynamically with smooth animation. Also, wide up enables applications to span across multiple displays. In short, Unified HMI version 3 shifts layout control from configuration-driven workflows to interact-driven APIs. Next, I'd like to show you a short demo that illustrates how these simplified APIs work in a real multi-display environment. So before start demo, I will introduce the demo environment. There are 3 displays, and the right upper one is Android tablet. 2 SoCs are used. The left one runs AGL IBI, and the right one runs a hypervisor with guest Linux. On Android tablet, Android 14 is running. All HMI applications you see here are launched and controlled using Unified HMI version 3 APIs. In this demo, API examples are shown on the left side, so please focus on how easily applications can be moved, resized, and rearranged dynamically across multiple displays. Okay, let's start. Okay, when I put the button, Android tablet layouts are separated to 3 parts, and application is moved to the separated display area 1. And when I push application launching button, Android tablet layouts are separate. GLMAX2 application is rendered on Android tablet display area 2. And please focus on the left command. This is very simple APIs. Run up GLMAX2 display area 2. So this means GLMAX2 is rendered on display area 2. GLMAX2 application is running on AGL IBI, but this application is rendered on Android tablet. And push other application button. Audio application is rendered on Android tablet display area 3. And push other button. And this button is implemented the wide up Navi display 1 display 2 command. So Navi display is span across display 1 and display 2. So it is very easily implemented like this command. And also, if you implemented some APIs at once, you can easily change overall layouts at the same time, like this command. And also, Unified HMI version 3 can dynamically move applications with smooth animation like this. So one more, start. Yes. So this is, I said, smooth animation. I will support this in Unified HMI version 3. And as more advanced use case, if you implement like this for loop and implement some animation, some continuous animation like them, you can easily make that animation, this AI agent penguin, move to this area 7, 8, 9 continuously. When using Unified HMI version 3, you can easily realize such this animation. Okay, thank you. This is all of my demo. Okay, next, I'd like to explain why Unified HMI is important for the AGL SODEV project. Unified HMI provides a common open source framework for multi-display virtualization. It enables unified layout control across different operating systems such as AGL and Android using a consistent approach. AGL SODEV serves as a reference platform for OEMs and developers, so I think supporting a wider range of multi-display and multi-OS use cases is very important. By using Unified HMI, AGL SODEV can flexibly support heterogeneous system configurations, including multiple virtual machines and operating systems like SODEV architecture, without introducing vendor-specific configurations. In addition, Unified HMI is continuously upstreamed to AGL UCB for some years and developed based on feedback from the AGL community. So this allows Unified HMI to continuously evolve as part of the AGL ecosystem driven by community feedback. And this diagram shows how Unified HMI version 3 can support SODEV architecture. Integration of Unified HMI is very simple, and you should install UHMI Manager on one virtual machine, like such as AGL API, and introduce UHMI Worker on all virtual machines and host VM. Each component runs as a system service, so once the environment definition file, JSON file is deployed to all VMs, Unified HMI is ready to be used. Applications can launch UHMI APIs from any node using gRPC protocol. gRPC protocol files are released on Unified HMI GitHub, so you can easily install APIs referring to them. As you can see in the diagram, Unified HMI version 3 can be integrated much more easily for developers and integrators than Unified HMI version 2. Here is our contribution milestone for 2026. In June, we plan to release the JSON creation tool on the Unified HMI GitHub repository. This tool simplifies the initial environment setup that I mentioned earlier. And in July, we plan to release the Android receiver implementation on GitHub. This is an important step towards supporting more heterogeneous AGL and Android use cases. In October, we aim to upstream Unified HMI version 3 to AGL UCB. And finally, at OS Open Source Summit Japan in December, we plan to demonstrate Unified HMI running on SODEV. Through these milestones, we want to make Unified HMI easier to try, easier to integrate, and easier to evolve together with the community. Okay, finally, I will introduce how you can access Unified HMI. The source code is available on our GitHub repository, and it's continuously upstream to the AGL USB master branch. So Unified HMI is also provided as a standard component of AGL, and there is a meta UHMI Yocto recipe for easy installation using AGL. Documentation is released on AGL documentation, so it can available to help you get started. So please give it a try to use Unified HMI in your environment. And we always welcome your contributions, reports of issues, and feedbacks. That's all of my presentations. Thank you very much.